All right, guys, we're ready to start. I want to thank everybody for calling in. Speaking of Fiber Optic Sensing Association, we're extremely excited for you to be here. Today, we'll be talking about the fundamentals of distributed fiber optic sensing. Next. But before the start, I'd like to talk to you, our presenters and people who are going to be working with today. My name is Nielsen Gabella. I work for Corning. I'm the Senior Global Market Development Manager in Technology Development. I'm also co-chair in FOSA. With us today, we have Gela Arendale, Market Development Director for Corning. Also, David Chen, Chief Technology Officer for GoPhoton. And Day Lang, Global Segment Lead, Security and Safety for Luna Innovations. So we have a great board for you guys today and a really fun agenda. Today, we'll start with a little welcoming, like I've done, and then we'll do a FOSA overview. What is FOSA and what we do? In addition to that, we'll have an introduction to DFOS, which Gela will cover. David will cover a backscatter phenomenon. Then Dan will cover types of DFOS with examples of distributed acoustic sensing, distributed strain, and distributed temperature sensing. All right. Then we'll have a little Q&A at the end. What is FOSA? See, FOSA is the members, thought leadership, shaping in the industry of fiber optic sensing. We are a nonprofit industry associated with formed in 2017 in Washington, D.C. What we do is all things fiber optic sensing. The key thing that we do is raise awareness and driving adoption for fiber optic sensing. We do technical webinars like we're doing today. We do advancing public policy and safety. We do a lot of that work in Washington, D.C. We also do a lot of educational webinars. We do a lot of trade shows as well. When we go there, we'll also do those webinars. And we do speaking engagements as well. Also, we do everything we can to promote our members. Like you see some of our members, we're presenting the information today. We have a global membership. It's open to those who invent, develop, make, install, support, and use distributed quasi-distribution fiber optic sensing. So it's not only for people who install it, but also with all ranges within fiber optic sensing. And we're very hands-on, share your voice type of membership. In which our members organize, manage, and collaborate regularly in a monthly and weekly calls. So let me show you a little bit of our members. Here's our membership, like you see here. Some of our top members here, like some end users. You see some people who do a lot of research, and then also some manufacturing companies. Go to next. So why is DFOS so important to not only what we do, but also in the market right now? It's an explosive market growth, as we can see here. The global distributed fiber optic sensing market demonstrates market expansion. As we see in 2016, that was a 600 million market valuation. But as we've seen in 2024, it exceeded 1.4 billion. And as we look into the projections into 2030, over $2.5 billion. A lot of opportunity in DFOS. This represents sustained growth driven by increasing infrastructure needs and security demands in the market. And as we go through these presentations today, as we talk about the basics, you'll see where these examples come with and what is driving a lot of this growth. All right. Next. And with that, I turn it over to Gela, who will do an introduction to DFOS.
Thank you, Nielsen. So my name is Gela Arendale, and I've been with Corning Optical Communications between Corning and 3M, which was acquired by Corning about over 27 years. So I'm happy today to be in the FOSA organization. Today, I'm a co-chair of the Technology Outreach Committee, and this is the type of work that we do in this committee. So what is distributed fiber optic sensing and what we call distributed or quasi-distributed fiber optic sensing? That's really a revolutionary leap in a monitoring technology. we are using optical fibers and converting that into a vast network of intelligent sensors. And this is enabling a pragmatic sensing solution across millions and millions of fiber optic cable kilometers worldwide. So in terms of, we'll go a lot more into the technology when David and Dane talk, but I'll just tell you the basics really, is that in distributed fiber optic sensing, the fiber itself becomes the sensor. So it's a continuous sensing technology. It uses advanced optoelectronic interrogators that inject precision-controlled laser light. So at various points along the fiber, there'll be these interrogator units. And then that system will analyze naturally occurring backscattering or engineered reflections. And David will go into the physics of what this backscattering is. It does enable, as I said, continuous monitoring of vibration, strain, and temperature, which Dane will talk about. And it really is a sophisticated processing of pinpoint events with meter level accuracy. The system basically uses only one fiber is required. And basically this fiber can be just regular fiber that you know of in fiber optic cables today. So what are some of the applications? And again, we'll talk about this as it relates to each of the technologies, but from a high level overview, this is really a very good solution for security and infrastructure protection. It can detect and track vehicle movements, human activity, and unauthorized digging. So you see there, it can monitor critical facilities such as international borders and sensitive installations. It could also provide a very early warning of seismic events and ground instability. So very important for early detection of earthquakes and some of the responses you would take. And then it can also do real-time leak detection in pipeline networks. So these are just some of them, and we'll talk a little bit more in the upcoming few slides. From an industrial and energy point of view, this also has some very important applications. DFOS can support downhole monitoring for oil, gas, and geothermal operations, and is extensively used in the oil and gas industry. It can ensure integrity of terrestrial and subsea power cable networks. So that also is extensively used across all of the subsea networks around the globe today. It can monitor the structural health of bridges, railways, and roadways, and can safeguard power stations and telecommunications infrastructure from unexpected events. So this breakthrough technology that utilizes fiber is really, as I said, achieves this continuous monitoring of distances exceeding 45 kilometers. It can operate without a line of sight requirements or remote power needs, which many other types of sensors today need. It often can utilize existing fiber. So if there is fiber there already, a spare fiber, we can definitely utilize that, minimizing the cost, and can deliver unmatched cost effectiveness per monitoring point when you consider the alternative types of sensing technologies out there today. So with this, I'm going to, that was a very high level overview, but now we're going to go deep, and I'm going to introduce you to David Chen from Go Photon, who will go into the physics behind this technology.
Thank you very much, Gayla. And also thanks to everybody on the call. This is opportunity. And I'd like to share some of the basic phenomenon also involves a little bit physics. Thank you. Next, please. Next page, please. Yep. Okay, so we go from left to right, left. So first, I just want everybody to take a look. It's the scattering. So before we talk about scattering, I just want to focus on to what we are trying to talk about today. It's the DAS, obviously. And you look at the picture on the right, you have the basic is a Mie scattering. So the Mie scattering is scattering about all the particles, and we separate into the different categories. Because this is a classic when the people say wavelength scattering, but also in the quantum level is a particle. So wave and particle nature is all together. So if you look at the Mie scattering, if the particle size and the dimension is close to in the range of the wavelengths, no matter what wavelengths you're in, it's close to, and then you have the basic Mie scattering. And you look at the symmetry of the scattering on the right, and then you have the Mie scattering for larger particle. The symmetry is more vivid. The unsymmetrical scattering is more vivid. Then we go to the Rayleigh backscattering, and we would like to see is more uniform. And because the scattering you see on the photo, this picture, you have the left and the right backscattering and forward scattering and all around. And what we want to do is trying to use the backscattering. I will cover a little bit detail on that. Why is the backscattering? And then on the left, our team like to deliver the message to you guys is, of course, light goes straight line. Of course, this is everybody's perception, and also we educated this way. But in the reality, the light goes in the least interacting way. It's a geodesic, if in the universe, in a gravitational wave. Those are well presented in the internet and in our college. So light interacts with the particles that causing all the scattering, whether uniform, non-uniform. That is the nature we can use. And scattering sometimes can be very much uniform, sometimes can be a little bit non-uniform. And what we do is we turn this scattering, this phenomenon, basic physics, applied to the fibers. And because the micro particle that's in the Rayleigh backscattering, and it's random. First is the scattering is random. Second is incoherent fluctuation, and it is elastic. That means the wavelengths you send it in, the scattered wave, it will be the same wavelength. So it's elastic. So you have no energy loss on the wavelengths. But of course, you have the scattering, you have loss in the fiber. That's what we can use. And then now, why the word is used backscatter? The backscatter, what we want to use is because you send a pulse into the fiber, and the section, once you send it out the pulse, you start to do the timing, and you sequentially do the timing. So each section of the scattering, you comes back at the receiver, the time can be recorded. So you see what we have used is OTDR is exactly recorded the fiber behavior at each section. And this is due to the nature we can do the timing, so we can precisely dissect the fiber into the sections we want to put our attention to. Next page, please. Yeah. Now, first what we want to use is the basic phenomenon. Since our childhood, we look at the sky, it's blue, and also see the sunset, it's red. And this is just the basic, it's covered. If you look at the overhead, the Rayleigh scattering is the dominant. And the Mie scattering, the intensity is being projected forward, so we don't see directly. Since the Rayleigh scattering is favored the short wavelength, so we see the sky is blue. So all the sunlight with all the spectrums, the short wavelength region, in the visible region, is get scattered, we see the blue light. And and if you look at straight, and of course some of the larger particles in the air, and so the forward loop of the me scattering is the dominant. That's why we see the white glares around the sun. And if you look on the left, we want to explain to you is the Rayleigh scattering. That's mostly used for the fiber sensing. And also we covered the other areas like the scattering is a Bruminen scattering and the Raman scattering. With all these three, we pretty much, like Gayla said, we can turn the entire fiber, lay the fiber under the ground into a sensor, into a big infrastructure monitoring tool for us. So with the Rayleigh backscattering, it's a photon scattering. It's an elastic scattering. Therefore, the wavelength is exactly as the wavelength you send it in. So if we send in 1550, we'll reflect the 1550. If we send a 1310, will be 1310. And if we send it a 1625, will be 1625. The beauty of this, okay, I like to emphasize the beauty of this. The beauty of this is that we can avoid the signal band. In other words, if we have the signal band at a 1550, we can send a 1310 or 1625. As far as the physics allow that we don't have to avoid the crosstalk, you can do this in parallel. In other words, the fiber is supports the signal, future internet, or the AIs, but at the same time, you can go send a signal using Rayleigh scattering, is linear scattering, and without interfere with the signal band. Okay, that's the beauty of Rayleigh scattering. Next page, please. Thank you. So the next one is we wanted to see is look at the atomic lattice structure. And look on the right, you have a laser comes in, and because the higher power, I want to emphasize the higher power. The higher power energizes the molecule vibration. So for the Raman, we basically talk about the vibrational mode or rotation mode. And if you look at the wave comes in, hits the red dot of that, and it starts oscillates, and it basically has absorption. The absorption turns into two pieces. So one is the Stokes Raman scattering. Other one is the anti-Stokes Raman scattering. One is converts to you absorb the energy, you have the second harmonic, you change the energy from the original to the a little bit longer wavelength, or the reverse to the shorter wavelength. And because this, we can using the Stokes or anti-Stokes peak to do the very precise temperature information sensing. And I think that there's lots of examples. We will cover this. And in the middle, you still see the Rayleigh scattering. So if the laser 1550, if the power is not very high, so the nonlinear phenomenon will not happen, and you have the Rayleigh scattering. But if you increase the power to a certain degree, then you have the nonlinear phenomenon, and the nonlinear phenomenon interprets into inelastic scattering. Then you have wavelength shift. So we can use that as well. Next page, please. Well, this one is a little bit more useful in terms of sensing because that has more features or structures, and we will cover this later. But this is called Bruminen scattering. The Bruminen scattering it's just a photon scattering. It is called the phonon scattering. Why? Because the whole lattice structure, the whole structure oscillates back and forth, and the oscillation direction is similar as the propagation direction, and that's why we call phonon. And for Bruminen scattering, for mass oscillation, we have the acoustic phenomenon, and that's called phonon. And if you have a charge displacement, you can called polariton. If the magnetic field displacement, we get magna. And all this is also non-linear phenomenon. The frequency shift is about, also you have Stokes, anti-Stokes. So you have about 1 to 10 gigahertz. And in the wavelength region, you have a 1 to 10 picometers of a pulse wavelength shift. And using this, we can more precisely detect the temperature. And why? Because the response is a little bit slow than the release scattering, because the whole structure moves, and we can using this is called structure, temperature, all good stuff. Next page, please. Great, thank you. So we, as industry engineers, especially in the early days, I worked with Corning and OFS and Prysmian specifically to design the fiber using the Bragg reflection grading, and we using the UV to artificially structuralize the fiber. And then when the temperature cycling, when the temperature change, when the vibration change, the acoustic change, this reflection, it will be more vivid. In other words, when we detect the signal will be more vividly seen. So either structure, temperature, and all those good stuff. And this is something which we can using called a special fiber at a certain region and a bridge in a certain areas. Thank you. Next page, please. Yeah, this one is the one I like to share a little bit with you, is because in the early days I worked with Corning, OFS, Prysmian to develop the bending sensitive fiber. Due to the nature of the fiber, the cord cladding, Corning and the rest are very smart to put some structure between the core cladding and to trap all the leaky mode, so you have much less bending loss. Because this artifacts, it causes the splicing. The OTDR sees this as artificial effects, and then the forward and the backward scattering is not symmetrical. Because this, I spend a lot of time with Corning and also the Verizon people and also the testing people. We trying to resolve those issues. Sometimes one way to do the tracing is not good enough. We have to do the bidirectional tracing. So at this today, we are just talking about the backwards scattering, so one direction. And that leads to the future I may talk about is the duality, or that's considered the emerging technology for the fiber sensing, which is will not be covered today. So I think I stop right here. Thank you, Gayla.
Thank you very much, David. And so that's a lot of the technology. Now we're going to go in with Dane from Luna Innovations, who's going to take this into the practicality of how this is used and the type of applications that we see from these technologies.
Thanks, Gayla, and thank you, David and Nilsson. So I'm going to talk a little bit about real-world applications. Thank you for that technical review, David. I'm going to refer back to that a little bit. You can go ahead to the next slide. So I co-chair with Gayla. I started my career in sensing back in 2015 and learned geophysics and signal processing. And then I got hired on at OptiSense in 2018. So when Luna acquired OptiSense, I came with it. At OptiSense, I took the role of a security subject matter expert. So I have some designations on that, some background there. And then I kind of oversee some of that application for Luna and all our other applications. So next slide, please. I'm going to explain how these different technologies are applied in a real-world case. So requirement for distributed acoustic sensing most of the time is real-time alerting. So if you can think about an event-based detection, we're looking for something and we have a plan as how to respond to that something whenever it occurs. If you can see over here on the right-hand side, there's a video playing. Let me orient you to all the little parts of it. On the far right-hand side, that's a map. You can see that the fiber is drawn along the map. That fiber line follows a pipeline where we engineered a burst disk. So this is a third-party validation flow loop test. And then we've pressurized a water pipeline there and have a burst disk fail at a certain pressure. So on the far left of the screen, you see two images. The green lines, the vertical axis is the amplitude or the signal strength. The horizontal axis is the fiber length there. And then underneath it, the yellow one, or excuse me, the blue one, has horizontal axis is the fiber cable, and then the vertical axis is time. So you see the intensity changes up in the top green graph, and then you can see color or contrast changes. So this is us taking vibrations and converting them, signal processing them, and then turning it back into acoustic information. So you'll see this video, it's on a loop. It's going to loop back up again in a second. Follow this solid line here. Right at the center of it, you'll see a negative pressure pulse or a shock wave occur when that casing fails or the burst disk fails. And then I'll explain what this screen is here. So it'll reset here. Slowly. Okay. So this faint horizontal line, this is just this middle screen here. This is just, there you go. That shock wave right there. Gayla, can you back that up a little bit? I'm sorry, I was talking over myself. Yeah. So if we pay attention right here, you'll see the shock wave from the burst disk failure. Right there, you saw it blip up here in the green, and then you see a very faint chevron or a V shape here. And then right at the center of the V, that is the product escaping at the location of the center of where that shock wave occurred. So we can infer two things: that the pipeline has failed, there's an open part of the pipeline, and the product is escaping. And then you see those two alarms right there. So that's a one real world application of DAS. Next slide, please. And Gayla, or I'm not sure who, somebody keep me honest on time here, because I can get long-winded. As David started off describing Rayleigh, again, Rayleigh is real-time based. So it's based on vibrations, modulating light. He talked about when fiber cables get manufactured, this is the way I think about it. When fiber strands are manufactured, there's tiny little imperfections, microscopic imperfections inside that glass tube. So we see a natural reflection because some of the photons are bouncing back, right? And so we see that based off of how the laser light's pulsed. So we can see that at certain locations along the fiber cable or the fiber strand. That's what makes this distributed. So instead of having thousands of point sensors or hundreds or tens or whatever you want to call it, we have a single fiber strand that software and this natural phenomenon, the Rayleigh scattering phenomenon, looks at certain points along the fiber cable. He ended his talk by talking about FBG. So when an FBG cable is manufactured, they etch in specific sensing points along the fiber on the inside of that cable. So it's similar to Rayleigh, but you can engineer in spacing for certain types of resolution if you want that along the fiber cable. And then once all this works together, you can send it through software like I just showed you with the pipeline leaking, and you can send real-time alarms that are actionable. So somebody needs to do something. Next slide, please. All right, so this is where it gets real interesting. So all of DAS, being that it's an event-based system, you can turn it really easily into a security and safety tool. It fits really well in that segment of those types of sensors. But it also fits really well in almost we could come up with an application in every one of the categories Department of Homeland DHS identifies as critical infrastructure. So chemical, commercial facilities, communications, manufacturing, defense, obviously, dams, EMS, energy, financial services, information technology, nuclear, transportation, waste and water and wastewater. There are applications for this technology, not just DAS, but the others in all those spaces. And then so the value behind this is it's got to be valuable to the customer and usable. So the customer has to know what it means to use this system. And it's new enough in some of these applications or some of the verticals that it still takes some training. So anytime you want to understand degradation of an asset or pay attention to either accidental or intentional damage to an asset, and this goes into, the bad guys. When the bad guys start planning how to do things, there's going to be surveillance going on. Hot tapping is a big problem outside of North America. It's been a problem for a long time. I'll go back to the pipeline analogy. These types of systems have been installed along pipelines to monitor for damages and terroristic threat for a long time before they were used for leak detection with DAS. So it works really well in any of those avenues. And then also the scientific side of it. So taking away from kind of the industry and commercial side, a lot of research and a lot of data can be gleaned from distributed acoustic sensing data. Next slide, please. Okay, so sort of some advantages in summary. The distances that we can measure are long. So this is relative to kind of what you think long is. So 100 kilometers, a little bit more than 100 kilometers. We're seeing all of the industry is pushing those distances out, extreme distances. But these systems can still do small distances. And in fact, a lot of the people I speak with, we're doing these for pipeline projects on 1, 2, 3, 4 pipelines. They're 4-mile pipelines. These are shorter type pipelines. So the application is kind of endless. You can get really, really, really small, but we have other instruments in the world of fiber optic sensing that can handle that stuff too. The head-end equipment is all in one location, and then the only thing in the field is the fiber cable. So the fiber cable is the only thing in the field. It's the sensing medium. In FOSA, we believe this is a very elegant solution. It's simple. You're kind of changing the way some things are done. I'll talk about that in a little bit, but it's a very elegant solution. And then one last thing I'll mention is you've got now the idea that you're going to have alarms from some of these systems. Is in general, these technologies will send alarms in an agnostic way to security type systems or sensor aggregators or SCADA tools or command and control tools. So we can send this information into another system. Next slide, please. Okay, I'm going to spend a little bit of time talking about distributed strain sensing. So the requirement here is for continuous high resolution strain measurement. So now we're getting more specific. I like to think of the DAS system. Most of the time, it's a turnkey system that's used to fulfill a requirement for an end user. This system is usually, this type of technology is used specifically for solving a specific problem. You can see over here on the right-hand side, you've got some rail lines that have buckled. So the industry has found that if you put a fiber cable embedded in the rail line, that you can obviously pay attention to compression or whenever that rail line starts to sag, if there's any reason that it's doing that. Again, these slow strain events are preceding a large catastrophic event. So that's the customers thought this through, end users have thought this through before they start looking at this technology. Next slide, please. David brought up Brouillon. Brouillon is used in this scenario to measure microstrain. Again, it's the way the light is changed by the events in the environment. Next slide. So when a customer is looking or a project requires specific strain changes for which alarms need to occur, that's when this is best used. So you can see a slide over here on the right hand. This is an example of some strain that slowly occurs over time after a pipeline's installed and the fiber's following a pipeline en route. You can kind of see some increased and decreased strain over a bridge. Later on, the data from this event, we actually saw a sinkhole forming, and the client didn't believe us. So it is very effective. And then really, again, you're monitoring for any incremental change that could lead to some type of a failure. Next slide, please. Okay, so where this works really well, ground movement in and around pipelines. Sorry. Subsea cables and umbilicals. On the pipeline part, when there's levees or there's dikes or there's earthen structures and there's pipes in those earthen structures, not only can we detect when the ground moves using strain monitoring, but you pay attention to the pipeline too, so you can get some preceding information. If the ground gets too wet or the ground gets too saturated, it may cause the ground, the dirt, to shift, and that may damage the pipeline. So again, the customers kind of thought all the way through this problem. In addition to subsea and umbilicals and the installation of those pieces of asset and infrastructure, monitoring post-tension on bridges and long-term wear, tunnels, safety in tunnels for structural integrity, foundation systems. And in another aspect, you can monitor vessels. So you can put the fiber around tanks or any type of vessel that's containing anything, and you can monitor for expansion or contraction. Next slide, please. Okay, and finally we come to distributed temperature sensing. So the requirement here is when there is a requirement for monitoring temperature across the whole fiber cable. So remember, we're measuring heat or an increase or a decrease in temperature in this case, or vibration. So you can think about a shock wave is going to travel all the way down either side of that fiber cable. The fiber is going to feel it. When the requirement is that you want to get a volumetric measurement of heat in an environment, that's when distributed temperature sensing comes into play. If you see the top little video that's playing here, that's just a temperature line, and you can see over time, as the laser lights is sampled, there's a decrease in this temperature here. And it represents the image down at the bottom. Again, going to the pipeline reference, the Joule-Thomson effect, or the JT effect, was discovered about 100 years ago. And it basically says when the pressure of a gas changes, the temperature changes. So if you've used any of those keyboard cleaners, the compressed air cans, and you've held it down and you had a really dirty keyboard, I've done too many site surveys and I got to really clean it off. That can gets really cold, and that's just a natural phenomenon. So that image right down there is a picture of you can see the pipeline, but there's a cold spot that has occurred in and around the event, around the location of the leak. Next slide, please. So DTS can use Raman, which was one of the ones, the third one David brought up, or Brian, based off of the needs of the requirements of the system. And really, it's as temperature increases or decreases, light movement changes in the fiber cable, and then gradually hot or cold spots can be felt or seen. Next slide, please. Safety. So we're talking about measuring of heat here. This is a segue into the way to think about DFOS, and this is something that's been used for a long time. It's kind of like the nervous system for an ecosystem. And in a mine, in this case, you've got a lot of that. So you would consider fire detection in and around anything that's going to create a hotspot. So it could be the electrical infrastructure. You've got fiber cable running through that electrical infrastructure and then going into each master control or power junction box. And you can you can detect the buildup of heat. That part of this is the key is that we're not looking for a flame, or no, we're not waiting for spontaneous ignition. We're well before that with DFOS. We're feeling the heat, and then as the temperature increases, there's a pyrolysis phase where things start to smolder and you actually get some smoke. So we're seeing that increase as well. And then, I mean, we're getting detection out here versus legacy types of fire detection technologies is waiting for the spark or the flame. Next slide, please. And then kind of in summary, heat monitoring, I mentioned throughout the whole bulk electrical system, battery storage, battery charging, runaway fires, that's a big problem. A lot more of our infrastructure is going electric. So if you think about problems in parking garages or charging stations for EVs, and then the other part of it that's really cool and that I've done a lot of this work this last 18 months or so, and it's all virtually set up. So there's a lot of engineering that goes into setting up a linear heat detection system whenever it's looking for fire, and it's connected to fire suppression systems. Sorry. We are not waiting for the cable to fail, basically, because the cable has to melt and fail, and that triggers the event. So this is all set up virtually, and then it's code compliant and fits in with all the fire code. And I think that's, yes, my last slide. So thank you guys.
Thank you very much, Dane, David. So we do have some questions that have come in, and so I will ask, maybe we get on video. I could then just kind of address some of these questions to the panel. So one of the questions that came in was, how are the interrogators installed? Either David or Dane.
How are they installed? They
Yeah.
are typically, these are rack mounted controllers. So it's a chassis with a laser inside it, and that's in a controlled environment just for them. You know, you want to keep it clean of dust and that kind of thing. So it's a rack mounted unit. Some of these units are getting smaller. So it just sort of depends on the manufacturer, and it kind of depends on the application, but it's usually mounted in a rack. There's some processing gear and some server gear associated with that. I guess that answers the question.
Okay, good. Second question I got is, if the fiber cables are not in place, what is the preferred cable installation method for sensing?
I can field that too, unless somebody else wants to.
Yeah, go ahead.
Dan, go ahead, please.
Okay, can you repeat it one more time, just so I make sure I'm
So
not.
if there's no fiber there ready, right? So what is the preferred cable installation method for sensing?
It depends on what you're monitoring. Again, so if you're monitoring a piece of infrastructure, so let's take the examples of power cables, pipelines, cable tray, you know, any sort of linear infrastructure that's already sort of established, right? The fiber just needs to be in the same environment or coupled to the same environment as the pipe. So if it's buried, or if this power cable is buried, then the fiber needs to be coupled to the earth that the pipeline is coupled to. It's a lot about, that's the way the physics work. The other point I might want to make is that, you know, you want to look for where the fiber is, but there's tons of fiber in the world. We're discovering this, and there's new ways to capitalize on this. When, for instance, if you're in a shared right of way, you may have an operator that's got some assets but no fiber, but you may have an operator that's what they have. They're the comms provider, or it may be a different provider that's got their own comms. So you can provide a multiple value across the board in that situation. For a long time, people were talking about smart cities, and that was a great thing to brainstorm about. And I think I was on some talks around that. So there's fiber everywhere in the infrastructure, and as when I've seen some of these cities are getting built up, master plan cities from the ground up, they're putting fiber infrastructure in place also specifically for sensing. So they're putting it next to roads, for instance, or in the embankment of a rail line if it's got if they're monitoring it for security or for monitoring the infrastructure of the rail, but so on and so forth. So it really depends on what you want. You want the coupling of the event. So if you've got a pipeline that's buried in the ground, energies that are in the ground are going to propagate pretty efficiently, and then they're going to hit the outer jacket of the cable, and then that's going to touch the fiber that's holding the light.
Actually, I'd like to add a little bit on that. Dan,
Yes,
wonderful response under this, because he's really good on using the infrastructure existing, so the cost is really low, and we can use the majority of the resources. So that's 100%. I agree. But at the same time, if the specific structure, let's say the bridge, the one of the pipeline edge, then we can install and can do is by using the budget to install the specialized fiber, like the fiber braided grading. So this will more specific, vividly reflect the phenomenon for structure, temperature, all those good stuff.
But that actually does lead me into the next question that we got, which is, what is the cost? Is there a significant cost difference between normal fiber and a fiber brag rating type of fiber?
Yes, but I don't know exactly how many times, but the process for making the special fiber cost is another domain. But this is the beauty is a small section, small increment to the environment that we want to deploy. So the cost maybe fiber itself is maybe a little bit higher, but the section is not so massive. Like the communication fiber is everywhere from A to Z, may stretch thousands of kilometers, but those one is only maybe a few kilometers, maybe only a few meters to this kind of range. So the cost sometimes
The
could be
beauty
very
really of what we've been talking about here is just using regular fiber, not the the fiber brag rating is specialized for specific applications, but most of everything we've been talking about today, right, Dane, is just using regular fiber, correct?
right. Mhm.
Okay. All right, this one is a more of a technical question, I guess. What is the largest elastic strain that can be measured? I don't know if either of you could.
I'm gonna let David answer that.
Okay, so if you want to take this, it's all about the largest strain. This is strain until the fiber breaks. So if you talk about the fiber can sustain, I'm talking about bending or pulling to a certain limit. That's the fiber can sustain. That's the limit that can the sensing will respond until the fiber really breaks.
Okay. Well, we have a lot of conversation going on here. I'm now looking at the at the questions, so bear with me here. I'm kind of going in order, but there's some follow-on questions happening too. In one question is, in the leaking detection example for the pipes, is the fiber cable inside the pipe?
No. So the fiber, it can be on the pipe. Again, we're not, a lot of these questions, so we probably have fielded these questions several times, right? Because this is how our brain works. We're trying to rationalize how this fiber is sensing in a pipeline, how is it getting information? So it literally is, you've got a pipe, regardless of what the pipe is made from, and honestly, to a degree, regardless of how big the pipe is. It can be a little bitty 6-inch pipe, it can be a big 42-inch pipe. Fiber cable needs to be somewhere in proximity to that outer diameter of that pipeline. In the DAS scenario, when the casing fails, there's a shock wave, and that shock wave is felt at the speed of sound in the product. So the speed of sound in gas is different speed of sound in liquid. And then you also have to calibrate speed of sound if you're in some sort of multi-phase situation. So you've got to change the speed of sound. And once you do that, you actually see a sound wave or a shock wave next to the pipe. But that's the shock wave, that vibration, that wave traveling through the product and through the pipe all the way in two directions at the same time, 600-ish miles an hour. So it's feeling that. And so that is a very unique event. And then if you have product leaking, so you have an energy source that's now creating a larger vibration here right at the center where that V occurs, you've got a casing failure and the product's leaking into the environment. That's DAS. For DTS, fiber's next to the pipe. It's probably a little bit closer because you want to get temperature resolution on it, right? And if it's not going to work if it's not going to have a delta, or if it's not pressurized. So that's why we go back to DAS. But if it's LNG or a lot of that stuff's getting put out there today, that compressed gas leaks out, and then you get that Joule-Thomson effect. And that's a different, I believe this is dual technology validation. So if you put a DAS instrument and a DTS instrument in, you can validate itself, right? So you can get a vibration alarm from the shock wave and the orifice noise, and then you get the temperature alarm whenever that occurs, when the product starts escaping. So the fiber just needs to be in that same environment. If these are assets that are above ground, then the fiber has to be mounted to the structure, so strapped to the pipe or strapped to pylons or embedded in concrete or however it needs to be. Did that help, Gayla, you think, or?
Oh, yeah, well, I hope so. I know we can't have live conversation here, but
Right.
please, everybody has their emails listed on this slide. So if anybody has a follow-on that you would really like to get answered, please do feel free to contact us either directly at FOSA or through any one of us.
Awesome.
So more questions because we have some more time. For those about to build new broadband networks, would it be advantageous to design in the location now so that the conduits and the fiber cables can be used for both Broadcom and for sensing?
I can take that again, or David, if you want to chime in too.
Go ahead, please.
Okay, Gayla, read that one more time.
So if you're about to build a broadband sort of network, your Broadcom network, would it be advantageous to design in the location now for sensing in the conduit and the fiber, so that you could use it for both Broadcom and sensing?
Yes. And there's not a lot of, in my experience, it's not that big of a lift, right? It's just, there's some things you can't avoid. If this is a roadside fiber and it's going, during intersections, or if you have other kind of crossings, the fiber can dip down 30 feet. I mean, 20, 30 feet sometimes. So super deep, below anything it would be used to monitor for on the surface. So you kind of have to, you can avoid some of those things. Fiber can sense in conduit, so that's been proven. Any type of tube, you just have to be, you don't want to go crazy. It can't be like a 5-inch HDPE and a little 1/2-inch cable. We've done testing with that, and there's been a lot of presentations on that, I think, with Duraline, right? So you can get the fiber in, and that was a lot of the premise, of us working with partners like Duraline and Orbia, is taking pre-installed fiber that's already in conduit and getting it smartly installed for sensing and communications.
There's more and more talk of this multi-use type of use of the fiber, right?
Yeah.
David, you were going to say something?
Yeah, I just want to add, wonderful. So that is just, this is the watching closely for the environment, how the fiber will be used. On the tester side is you can put the test equipment on a setting is in the controlled environment, CO, and also the HUD, or it can be in the field if you have a handset to do this as well. And what I will recommend is be careful, because that's like we all talk about today is using backscattering. So if we are using the backscattering, then we have to be careful. We don't need to go through the amplifier, because if the metro and access and also FTTH, the building the infrastructure, if they're using the specific amplifier to boost the signal, then they have a specific isolating there, and that will prevent the backscattering. So avoid those things.
So I guess there was a question in here, and I think you were addressing this, Dean, a little bit about the distance limitation and, how you can, if you're using legacy telecom cables to do the DTS or the DAS, what are there any present distance limitations?
Yes, I emphasize this is a very important. This is a wonderful question, an absolutely wonderful question. Number one is talk about the cost, right? The cost and also the safety. So we all know what Dan has said about all the wonderful applications is specific for the Blumenthal scattering, Raman scattering, and using nonlinear phenomenon. So therefore, the launch power has to be very high. And so sometimes in the field, the technician has to be very careful and not look for the safety. So for telecom applications, basically talk about a 1M class, those type, and also the cost is low, because the lower power. Mostly we talk about a 45 kilometers to 50 kilometers is the range, and beyond that, let's say 80 kilometers is really stretching, and so we try to avoid that. And specifically on the Raman is very high power, and the Blumenthal is also very high power, and the cost is very. The equipment for relay scattering, OTDR, versus the Blumenthal scattering and Raman scattering, the price difference is the cost is very different. So that's why we are talking about a more practical and cost-effective use is about a 45 kilometers to 50 kilometers range.
Very good. One question, it was a follow-up on another one that we had from this gentleman, but you know, he was saying, you know, based on his previous question about, you know, where do you do it? Is there any specific, and I think we addressed the, you know, that conduits and microducts can be used and versus also we could also do direct bury. I think there's even some application that could be aerial from what I know. Is there anything about gel versus non-gel fill cable? From your opinion, I know that we typically recommend gel filled, but
Yeah.
I believe you can do either, but.
So I'll go back to, you know, I lived in the DAS world, the distributed acoustic sensing world, solely for a little while. And we were really, it was really important for us in those early, or my early stages in this. Gel filled propagates that vibration. The opposite of that is gel free, and it could be powder. I mean, Gail, there's all different variants in there, right? So it deadens the vibrations once the vibrations hit the jacket. So in between the jacket and the fiber core, just that small amount of space, it deadens enough signal that the DAS can be less useful. Now DTS doesn't care for that. So DTS would be looking for temperature changes. So it's a little bit different. I think that there are some considerations for construction, probably based off of the environment that the cable is going to be in. So double armored, single armored, you know, those kinds of things. And then there are some considerations for increasing performance with a cable that might be better for a specific DAS, DTS, or DSS. Does that make sense?
David, or even Nielsen, I don't know if you have a comment to make here too.
No, that was great, Dan. Yep. I mean, I think the key here is, I think like Dan was saying, I think gel might give you better range or reach, kind of like you were saying about the microduct, right? If you use a huge microduct, then you're not going to get a lot of range. If you use a smaller microduct, that's going to help. It's going to get a lot more range, right? I think gel free or gel, that's what you're going to get. You're going to get, it seems you get better range with gel because of the compounding close to the fiber.
Good. And one question that did come in, I'm looking at it, is about the aerial. I know I just said I've heard it, but can this be done aerially?
Oh, yes, absolutely. So I'll let Dan answer that after. The area is basically the wind, the snow, the rain, all those are causing the vibration. So, and the DAS definitely specifically using Rayleigh backscattering can quickly detect all those vibrations. And of course, the rest of the temperature sensing structures also as easily to be detected.
I'll agree with David.
Good. Well, let me tell you, I haven't even touched every single question, and I feel like we're up on the top of the hour. So I just wanted to thank everybody for their time and for their very, you know, interactive questions here. We will look at every question that we've received and at least try, you know, as an organization to get back to you with an answer if we haven't addressed it already. But also each one of our emails is here, as I said earlier. So please feel free if you want to continue this conversation with anybody on the panel or within FOSA, please let us know. So with that, if you are, I'll just give one last plug. If you're interested in joining FOSA, Fiber Optic Sensing Association, as Nielsen said at the beginning, we're not reserved for only the equipment manufacturers or the fiber. We are open to users, end users, contractors, everybody. So please do reach out to us if you're interested in joining, and we can send you a package of what that will entail. And with that, I will close the webinar. Thank you very much, everybody, for your time.
Thank you.
Thank you.